This is lesson 7.3, simplifying complex rational expressions. Our learning objectives are to simplify a complex rational expression by writing it as division, and then next to simplify a complex rational expression by using the least common denominator, LCD. Great, so we're going to learn how to simplify complex rational expressions in two different ways today. And little reminder for you, in the previous lesson 7.1 and 7.2, we learned how to multiply, divide, add, and subtract rational expressions. And those skills are useful for today's lesson. Now, a complex rational expression is a rational expression in which the numerator and or denominator contains a rational expression. And a little reminder for you, rational means it forms a ratio, right? So the first five letters of rational is ratio. A ratio in math is a fraction, and it's a fraction of polynomials. So when it's a complex rational expression, well, we've got a rational expression in the top of a fraction and a rational expression in the bottom of a fraction. So it's complex because it's a rational expression within a rational expression. And so here are some examples of those types of complex rational expressions. So there's one example. Here's another example. And here's even another one. And today we're going to learn how to simplify these. And so let's get started. I have a quick how-to step process of how to simplify a complex rational expression by writing it as division. So step one, simplify the numerator and denominator. Step two, rewrite the complex rational expression as a division problem. And then step three, divide the expressions. And you'll remember that to divide rational expressions, we actually turn it into multiplication by keep, switch, flip. So this first example that I have for you here today, let's practice the keep, switch, flip method. Okay, so we're going to dive into a handful of examples. And when I see a rational expression divided by a rational expression, I keep the top expression the same. Okay, so we'll say keep. And then the division, we're going to switch it to multiplication. Okay. And then the bottom fraction, we're going to flip it, meaning we'll take its reciprocal. And so this division problem, right, this is a division of two rational expressions, it's going to become a multiplication problem. So I will rewrite it as 6 divided by x minus 4. Right, that's the top fraction. I'm keeping it the same. I switch division to multiplication, and then I take the reciprocal of the bottom fraction. And so my 3 that's on top of this fraction, it moves to the bottom of the fraction. And then the x squared minus 16, it moves to the top of the fraction. But one thing that we also want to do as we keep, switch, flip is we want to factor. And so you'll notice this is the difference of x squared minus 4 squared, right? So I have 16, it's 4 squared. So I'm going to factor the difference of squares. And so we write the x and the 4 at the start and the finish of two binomials, and we separate them with addition and subtraction. So we have now factored the difference of squares. And now at this point, since everything's in terms of factors, everything's factored, we can cancel factors that are common on top and bottom of our fractions, since everything's multiplication. So I notice there's an x minus 4 and an x minus 4 on top and bottom, so those terms cancel. And also, I see a 6 divided by 3. So this 6 divided by 3, boom, boom, that reduces to 2 divided by 1, right? That's a reducible fraction. And so my final answer is, well, the 2 that's left over on top and the factor of x plus 4, right? Those factors are the things that are left over. On the bottom, there's division by, well, a 1. That was all that was left. But dividing by 1, we can make it invisible. And this is the final result. Great. So that was a reminder for you about how to, keep, switch, flip. Okay, when you have division between two rational expressions, two fractions, then you can do a keep, switch, flip, and it makes your life much easier. Make sure to factor along the way. Okay, now let's go ahead and move into a next example and discuss maybe why this example is different than the previous one. So here I see 1/3 plus 1/6, and that's divided by 1/2 minus 1/3. And so I see two fractions in the numerator separated by addition and two fractions in the denominator separated by subtraction. And so you would say, well, can we keep, switch, flip? And the answer is not yet. First, we have to combine fractions together. So first we have to simplify this into one fraction, and then simplify this into one fraction. And once we have a single fraction divided by a single fraction, we can then keep, switch, flip, and proceed. Okay, so this is an example without variables. All it has is numerical values, and I'm going to show you the process to get this done. And so you think, well, I need to add these fractions together, but to do it, we need a common denominator. So we look at the denominators 3 and 6, and we say, what's the LCD of 3 and 6? And the answer is 6. Because if I multiply this 3 by 2, okay, I get a denominator of 6. But then that means I have to multiply the 2 on top and bottom of this fraction. Great. So I have made it so that those denominators 3 and 6 become the denominators 6 and 6. And now I look at the bottom two. Okay, so now addressing the denominator, right? And I have 2 and 3 here. And so I think to myself, what is the LCD of 2 and 3? And that is 6. And to make this denominator become 6, I have to multiply by 3, but that means I have to do it to the top as well. And to make this denominator become 6, I need to multiply it by 2. So I multiply 2 on top and bottom. Great. And so now I have been able to make everything the same denominator. Let me show you what I've done. So applying the multiplication, 2 times 1 is 2. 2 times 3 is 6. And then I have a plus, and then that's 1/6, right? That didn't get changed. And now looking at the bottom, 3 times 1 is 3. 3 times 2 is 6. I have a minus sign. 1 times 2 is 2. And 3 times 2 is 6. Great. And so now I can do the addition of these fractions, right? 2/6 plus 1/6, that's 3/6. Remember, when you are adding fractions with a like denominator, we add the numerators together, right? 2 plus 1 is 3, and then we keep the denominator the same. Okay, and now looking at the bottom, 3 minus 2. 3 minus 2, that gives me a 1, and that's over the common denominator of 6. Great. So now I have a single fraction divided by a single fraction, and I can do the keep, switch, flip process, right? So I'm going to keep this fraction the same. I'm going to switch this division to multiplication, and then I'm going to flip this fraction. Okay, and the result is, well, 3/6 times 6 over 1, like that. Okay, and so now it's time to multiply these two fractions together. And, well, one cool thing is that the 6's cancel. That 6, it cancels that 6 on top and bottom, right? That's a common factor of the numerators and denominators. So the result is 3 over 1, which is just 3. 3 divided by 1 is 3. Great. So this is a fun little example that didn't have any variables. It's just, fractions we're used to from elementary, middle, and high school. And we taught you, hey, how can we simplify this complex rational expression? And, we found common denominators, finding the LCD in both cases, right? And then we rewrote it, and then we simplified the fractions, and then we did a keep, switch, flip to turn fraction division into multiplication, and then we were done. Well, let's try the same process except instead of having just all numbers, we need to include variables. So this complex rational expression has variables like x and y. All right. So I'm going to help you make sense of it. And the first thing we want to do is we want to combine these two fractions into one fraction, in this numerator. And then we go down to the denominator and we want to make these two fractions one single fraction. And to do that, we need a least common denominator. And, and so I look at the denominators here, x and y, and I say, well, this denominator needs a y, right? It's missing the factor of y. And then this denominator needs an x. It's missing a factor of x. And so that's why I have multiplied y here. I had to apply it to top and bottom. And then x here, I applied it to top and bottom. And now we have the same denominator, right? Y times x is the same thing as y times x. We've got a common denominator. Let's do that now to the very bottom stuff. So we'll do the same process to the denominator here. This y here, and this x, those are the factors of the denominators, and so this y is missing an x, so I multiply x on top and bottom. And this x is missing a y, so I multiply y on top and bottom. Great. Let's kind of clean this all up and see what results. So I've got a y times 1, which is y, divided by a y times x. And then that's plus 1 times x, which is x, divided by y times x. Okay, and that's all divided by, well, x times x is x squared. And that's divided by x times y. I can just write x times y. And then I have the minus sign. And then y times y is y squared. And that's divided by x times y. Okay, and so now that I'm here, I have a common denominator, right? Here and here, common denominator, and here as well. And so now I can combine stuff. I can say, well, I'm going to turn this into a single fraction on top of y plus x, and that's over yx. And that's divided by, well, this fraction, x squared minus y squared, and that's divided by, well, x times y. So there we go. We've gotten to this point. And one thing to take note of is, y times x, that's the same thing as x times y, right? Multiplication is commutative. So if it makes you feel better, you could turn this y times x into x times y so that these things look like they match now. Okay? Now, let's proceed. And maybe now we've reached the point where we can keep switch flip because we've turned this stuff into a single fraction, right? One fraction divided by another fraction. So let's apply keep switch flip, and we'll proceed from there. Great. So if I do that, and I'll do that down here below, I get y plus x over x times y. And that's times, right? I'm switching to multiplication. But I have to flip or take the reciprocal of the bottom fraction. Right, so I've taken the x squared minus y squared over x times y, and I took its reciprocal, so the x times y is now on the top. X squared minus y squared is on the bottom. And we get to this point, and there's something that makes us really happy, right? Because these are all factors, right? These are all factor pieces. Boom. It looks like I can factor this bottom right. That's the difference of squares. We'll get to that. But I do notice that this factor of x cancels this factor of x. And this factor of y cancels that factor of y. And so that started to clean things up for me. And so now I can write this as y plus x divided by, well, x squared minus y squared. But at this point, you can say, well, this is the difference of two things that are squared. And so I'll write it as x plus y times x minus y. There's the difference of squares. And then there's one thing that you might observe. Well, if you're adding two things together, it doesn't matter the order with which you add them. Addition is commutative, just like multiplication. So y plus x is the same thing as x plus y. And that might be nice for you to just swap them, right? Now, you can't do that if that was a minus sign between them. It's only because there's addition between them that you can do this. But what you then notice is that there is a common factor on top and bottom. The x plus y on top cancels the x plus y on bottom. And whenever you cancel everything on top or on bottom, there's an invisible one that is there, right? That was 1 times x plus y. And when you cancel the x plus y, that invisible one has to appear. And then you can write your final answer as 1 over x minus y. X minus y was the only factor remaining in the denominator. So there we go. Let's make that minus sign nice. There we go. All right, so this complex rational expression that we started with here in black, it simplifies to 1 over x minus y. That's how simple it becomes, right? And looking back, this complex rational expression, it was really just 3 in disguise. It simplified. So this is the same thing as 3. It equals 3. So sometimes complex rational expressions, they really get simplified. They're not complex anymore. They've simplified to something nice and easy. Well, let's go ahead and now address maybe a more complicated situation. Okay, we're increasing complexity as we go. And so here's the next scenario. It's n minus 4n over n plus 5, all divided by 1 over n plus 5 plus 1 over n minus 5. And so my objective is going to be to create a common denominator for, both the top and the bottom of this big fraction. By the way, it's nice to write, if you have some value, not set up as a fraction, subtracting a fraction, well, you can turn this into a fraction by dividing by 1. And then your brain sees these two fractions. This is a good practice. And so now I look at this stuff and I say, well, I need to get a common denominator of, well, the LCD of 1 and n plus 5. And so 1 and n plus 5, their LCD is just n plus 5. So I can multiply an n plus 5 on top and bottom of this fraction that I now have, right? Cool, done. Well, let's look down in the bottom. Okay, I have an n plus 5 factor and an n minus 5 factor. And so this factor is missing an n minus 5 that the other, denominator has. So I can multiply on an n minus 5 here and here, top and bottom of this fraction. And now this denominator, it's got an n minus 5. It's missing the other denominator's factor of n plus 5. And so I multiply an n plus 5 on top and on bottom. And it will make more clear sense why we're doing this as we write stuff out. What we're trying to do is get a common denominator so that we can combine two fractions into a single fraction. And that's what we have to do before we can keep switch flip. Great, so I'm going to write this all out. And let's keep this separated from the last problem here. Let's just go whoosh, whoosh, whoosh. Okay, so now I'm looking at this and I have, well, n times n plus 5 here, right? So you could think, oh, I need to distribute. And I'm creating a big fraction with a smaller fraction on top. And a smaller fraction on bottom, like this. So this is my setup for the whole thing. And, well, let's see, n times n is n squared, right? N times n, that gives me n squared. And then I have n times 5, that gives me a positive 5n. Okay, and then I've got this minus sign, and I'm subtracting off 4n, like that. And the common denominator of this all is n plus 5. That's the common denominator between these two fractions, n plus 5. Okay, so we've combined the two fractions of the numerator into a single fraction now. Let's go ahead and look at the denominator. Right, so I'm looking down here now, and I've got a common denominator of n minus 5 times n plus 5. That's my common denominator. I could write that right now if I want to. And let's clean up the numerators. So this 1 distributes into n and negative 5. So 1 times n is n, 1 times negative 5 is negative 5. Now I see this plus sign right here. Right, so I know I'm going to be adding these pieces. I'm going to distribute the positive 1 into both of these terms, right? That's a positive 1 times n. So I get a plus n. And then positive 1 times 5. It's a plus 5. Great. So all of this stuff right here, right, has now been combined into a single fraction divided by a single fraction. And yeah, you understand why I did that, because now I'm going to keep and then switch and then flip, right? That's what we've been doing this whole time. So I've got the n squared plus 5n minus 4n, and you might notice I can clean it up as I go. Positive 5n minus 4n, that's just a 1n, right? So this all is just n. And so I get an n squared plus n, and that's divided by n plus 5. And now I've done a keep, now I switch, and now I flip. And so I take n minus 5 times n plus 5, those factors of the denominator, I put them in the numerator. And something I notice as I clean this up a little further is this negative 5 and this positive 5, they cancel. Negative 5 plus 5 is 0, and n plus n is 2n, like this. Great. And now I'm going to analyze this stuff a little bit and say, well, I've got n squared plus n. Is there a GCF that I could factor out of this? The answer is yes. I can factor an n out of this stuff. Okay, and so n squared plus n simplifies, and I'll write it above, simplifies to n times n plus 1 when I factor. Okay, and so now that everything's fully factored, you might observe with me that, wait, I've got an n plus 5 factor that cancels on top and on bottom. I can cancel the n plus 5s on top and bottom here. And I also have the n factor, right? This n, see, it cancels that n right there. Okay, so I've gotten cancellations to occur. And now I'm going to write my final result with the remaining factors. Okay, so I've got this fraction that I now have as just a single fraction, and it has n plus 1 and n minus 5, and those were the only factors left in the numerator, and then 2 on the bottom, right? That's the only thing left on the bottom is this 2 right here. And so my final answer is n plus 5 times n minus 5 divided by 2. Great. And so here we have simplified a variety of complex rational expressions together. Well, let's go ahead and move on to our next learning objective, which is actually to do the same process, but perhaps you'll find this new way easier than the way that we just addressed. Okay, so we're going to simplify a complex rational expression by using the LCD. And to do that, here's the three-step process. Step one, find the LCD of all the fractions in the complex rational expression. Then step two, multiply the numerator and denominator by the LCD. And step three, simplify the expression. And we are going to use expressions that we've already seen. So we've seen this expression already and simplified it earlier, and we saw this expression earlier, right? That was part of our previous examples. Like that was this expression here and this expression here. So we're gonna look at a new way to simplify them and see if you like this way better. Great, so I see 1/3 plus 1/6 divided by 1/2 minus 1/3, and my goal is to find the LCD of all the fractions in the complex rational expression. So I look at 3, 6, 2, and 3, all the denominators. 3, 6, 2, and 3, their LCD is 6. And so once I find the LCD of all the denominators, I multiply everything on top and bottom by 6. And why is this so good? Well, because it helps me get rid of fractions. Multiplying fractions by an LCD clears the fractions. And so multiplying, 6 into this first fraction and second fraction on top, what do I get? Well, I get 6, and I'll help you. 6 divided by 3 times 1. This is how you do it. 6, take that value, divide it by the denominator, and multiply by the numerator. 6 divided by 3 is 2, and 2 times 1 is still 2, right? And you could think of it as, what's 1/3 of 6? Well, 1/3 of 6 is 2. Okay, and now do the same thing to the second fraction. 6 divided by 6 is 1. And then multiply that with the numerator. 1 times 1 is just 1. Great. And we had addition between these values. So what just happened? I multiplied by the LCD of 6, and it cleared these fractions so that they're not fractions anymore. Let's do it to the bottom. Let's see how you do. 6 times 1/2. Well, yeah, that would be 6 divided by 2, which is 3, times 1. So that 3 times 1 is just 3, right? Now I have the minus sign, right? Pay attention to the signs. And then I proceed and I multiply 6 with 1/3. And I say, well, 6 divided by 3, that's 2, and 2 times 1 is just 2. So I put a 2 right there. All right, so I have just multiplied every fraction by the LCD, and I got this. And 2 plus 1, well, that gives me 3. And then 3 minus 2, that gives me 1. And 3 over 1 is 3. And this is the exact answer that we got previously. So a question comes up, which method do you prefer? Do you prefer, the previous method, or do you prefer this one? Let's look back. You see here, this is the process we used to solve this to get 3. So we went through that whole process. And here, this is the process that we just used to get the same answer. Your choice. You can decide which method you would like to use. And in fact, sometimes one method is actually better than the other method and will make your life easier. So one method's not always better than another method. In this case, it looks like this method, multiplying top and bottom by the LCD was much easier. Cool, let's move on to this next example and do the same thing. So this is a complex rational expression that we already saw earlier. And our goal is to multiply the entire thing, the top and bottom, by the LCD. And we ask, what's the LCD of all the denominators? X, Y, Y, and X. Right? These are all the denominators. And so what are the factors that they have? Well, there's an X, right? So X, and the only other factor is Y. So I have the Y. Okay, that's the LCD, X times Y. And so I multiply that LCD on top and bottom. and I distribute, right, to this and this and this and this fraction. And as you go, you can think, well, what are we doing? We're going to multiply x times y over x. So this x right here cancels that x, right? Because that's technically in a numerator, denominator, these cancel. And so really, you just have y times 1. In other words, y, right? Y times 1 is just y. Okay, let's go ahead and multiply into the second fraction here. So we're going to multiply x times y times 1 over y. And this y cancels this y. And so x is multiplied with 1, and you just get 1x. And there was addition between these terms, so we're going to keep the addition sign. Great. So that all simplified to just y plus x. Let's look at the denominator now. Right? We're looking at the bottom of this complex rational expression, and we are going to multiply x times y with x over y. And this y cancels that y, right? Because this is y divided by y cancels. And x is multiplied with x to get x squared. Then we have the minus sign. And there's the minus sign. And now let's go ahead and multiply x times y, multiplying it with y over x. Well, the x cancels that x of the denominator there, and y is multiplied with y to get y squared. And there we have it. All right, so we have just distributed the LCD into every term of the complex rational expression, and this is our result. And at this moment, we could notice, hey, that's the difference of squares, so we can factor. Let's get out our factoring skills. Factoring the difference of squares, we would put, x and y in two binomials like this. And then we'd separate them with addition and subtraction. Those are conjugates. Conjugates are when you have the same values, right, x and y, with opposite signs between them. And looking at the top, y plus x, well, to make your life easier, we could write y plus x as x plus y, because addition is commutative. It doesn't matter the order with which you add things, so we can make that switch. Why would I want to do that? Because then it makes it really clear that I've got this x plus y factor on top and the same x plus y factor on bottom, which cancel each other. Great. Please remember, when you cancel anything on top and bottom entirely, right? When you cancel all the factors of the top or the bottom of a fraction, there's an invisible 1 that appears, because that invisible 1 is part of the final answer. So we get 1 over x minus y. That is the result. Great. So looking back, we had answered this question earlier, right? We had done this same type of problem. Okay, and looking at it, this is the way we did it, right? Here's the process that we used. We got a common denominator of the top, common denominator of the bottom, and then we, rewrote the whole thing, and then we combined the fractions into single fractions, and then we did keep, switch, flip. But then we still had to get out our factoring skills, like we saw the difference of squares, and we ended up with the 1 over x minus y that way. And then here was us doing our new method of multiplying everything by the LCD right at the beginning of the problem, right? Multiply everything by the LCD. It simplifies to this. Then we got out our factoring skills to see that things canceled, and we had our answer. So the choice is yours. You could think to do it in either of those two ways that we've described so far today. Let's go ahead and try another example. And by the way, we just have a few last examples that we're going to be looking at. And these are increasing complexity at times and just trying to help you build your skills in seeing how to do this. So looking at this example here, I have 2 over x plus 6 all over 4 over x plus 6 minus 4 over x squared minus 36. And I look at all the denominators. That's one thing I analyze first. I look at the denominators and I say, what is their LCD? And it may become a lot clearer once you notice the difference of squares. This x squared minus 36 is x plus 6 times x minus 6. So you have to factor the difference of squares. And then you notice, well, all of the denominators have an x plus 6, but they don't all have an x minus 6. Okay, so what I have to do is multiply the top and bottom of these rational expressions with the LCD. And the LCD, least common denominator, is x plus 6 times x minus 6. Those are the factors that we saw, right? We saw x plus 6, but we also saw x minus 6, and so that has to be a part of it. And so I'm multiplying these factors, the LCD's factors, to the top and bottom here. Great. And so now that I've set things up, let's go ahead and write everything out nicely. So we're going to be getting rid of the fractions, right? If you picked the correct LCD, it gets rid of the fraction on the top and it turns it into just an expression that's not a fraction. And the bottom will not be it won't have fractions anymore. It's kind of cool. But what you do have to observe is that this x plus 6 is going to, multiply in here, but it cancels this x plus 6 in the denominator. So look at the common factor of what you're multiplying in and what's in the denominator, because those cancel. Okay? And so we're multiplying this 2 by x minus 6. That's what's remaining. Cool. So all this stuff cleans up to 2 times x minus 6 because the x plus 6 factors, they cancel. Now looking at the bottom, we have an x plus 6 that we're multiplying in, and that's the division by an x plus 6. So the x plus 6 factor cancels the x plus 6 factor, and this 4 is multiplied with x minus 6. So I put a 4 times x minus 6. Now I have the minus sign that's right here, so I'm going to put it, right? That minus sign just goes right there. And now I look and I say, well, moving on to this fraction, it has a denominator of x plus 6 and x minus 6 factors. And that's what I'm multiplying into this stuff. So x plus 6 cancels x plus 6, and x minus 6 cancels x minus 6. And we're left with just 4. That's all that's left, 4. Okay? So one at a time, we are finding, these factors that we're multiplying as the LCD are canceling some of the things that we observe in these denominators, and that makes it really easy to write out the result. Okay, so there we have it. We've now turned this thing right here into just this stuff. Great. And to finish, we now need to, kind of clean this stuff up and see if we can make it look simpler. Okay, so we've got the 2 times x minus 6 right there. And one thing I can think of is I notice that both of these are a factor of 4, right? 4 and 4. I could factor, and technically this is a binomial, right? Here's the first term and here's the second term. So I can factor a 4 out of both of those terms and I'll get an x minus 6 minus 1. Okay, so what did I just do? I pulled a 4 out of this and this, boom. And I'm left with just the x minus 6, and then pulling a 4 out of 4, there's a 1 left over. And now let's see, can I cancel anything? Well, yes, this technically will reduce this fraction of 2 over 4, since they were factors, is just, well, 1 over 2. It reduces to 1 over 2. And so my final answer is going to be, well, x minus 6 on the top, and then the 2 times, well, this is x minus 6 minus 1, so I could combine these constants. Negative 6 minus 1 is negative 7, so I have an x minus 7. And this is my final result. Let's look at some more. So looking at this complex rational expression, I would first think of factoring this denominator right here, this m squared minus 7m plus 12. Well, what does it factor to? Okay, so isn't that going to just be like m minus 3 times m minus 4? Looks like it. Why am I saying that? Because negative 3 times negative 4 is positive 12, and negative 3 plus negative 4 is negative 7. Okay, so I was able to factor this trinomial into these two binomials. And I'm actually really surprised because those same factors that I just found are the factors of these denominators, m minus 3 and m minus 4. So what is the LCD of, all this stuff? The LCD is m minus 3 times m minus 4. Those are the factors of all the denominators. Okay. Let me clean this up just a little bit. M minus 3 times m minus 4. Great, so I'm going to be multiplying this as the LCD, the least common denominator, to the top and bottom of these fractions. And let's clean it all up. Let's see what we get. Well, m minus 3 cancels m minus 3, and m minus 4 cancels m minus 4. And all I'm left with is this 4 for this fraction. Great, that was nice. That made it easy. And now looking here, down here, okay, we're now going to address this stuff. Well, this m minus 3 right here cancels this m minus 3 when I multiply this LCD into this fraction. And so this m minus 4 gets multiplied with this 3. In other words, I've got 3 times m minus 4. And then I have the minus sign right here. Yeah, that minus sign, I'm going to write it. And now I'm going to look at the second fraction. This second fraction, it's multiplied with the LCD, but this m minus 4 cancels this m minus 4. And so this 2 is multiplied with the m minus 3. Great. Okay, so here's my result that I currently have. And all I'm going to do is, kind of clean up this denominator. So I'm going to distribute. And I'm left with, what happens when I distribute? 3m minus 12 minus 2m plus 6. That's what I get when I distribute. Yeah, and I've still got that 4 on top. And lastly, let's combine like terms. Well, 3m minus 2m is just 1m, and negative 12 plus 6 is negative 6. And then I've got that 4 on top, and I'm done. This is the final result. All right, so let's just address one more for funsies. Great, here's the last one. And I see let's start analyzing the denominators. Y plus 1 for this denominator, y minus 1 for this denominator. And you know what? Let's just divide that 1 by 1 to create a fraction, right? So that we can see what its denominator is. Its denominator is 1. Okay, so anytime you see an integer, turn it into a fraction by dividing 1. And let's go ahead and now multiply the top and bottom of this rational expression by the LCD, the least common denominator. Well, isn't that y plus 1 and y minus 1 and 1? Yes, it is. So we have the y plus 1 factor and the y minus 1 factor. And the factor of 1, I can make it invisible, right? 1 times that stuff is just that stuff. So we don't need to worry about that one. But we're going to now multiply the same stuff down here. Great, and this will clear all of our fractions. making it so that we have gotten rid of fractions. That's what's so great about multiplying the LCD. And yeah, this y plus 1, it cancels that y plus 1. And so y is multiplied with y minus 1. Okay? So that's why I'm writing right here, y times y minus 1. Okay, and now moving forward, well, these don't cancel this at all. So this 1 is multiplied with y plus 1 times y minus 1. Nothing canceled. So I write y plus 1 times y minus 1. Great, now moving on. And I have a plus sign. I now look at this fraction. I'm multiplying these factors by this fraction. And you'll notice the y minus 1 factor cancels the y minus 1 factor on the bottom. And so y1 is multiplied with y plus 1. Y plus 1 times 1. Right? That's why I'm writing a y plus 1 right here. Cool. All right. So there you go. And now our remaining objective is just to kind of clean this stuff up, right? Our remaining objective. Let's just take our result, start to clean it up, and see how it simplifies. And so looking here, I might think to FOIL this, right? First outer inner last multiplication of two binomials. And so I'll do that for us. And that becomes, what, y squared minus y plus y, and then minus 1. Okay, so I just FOILed this stuff. First, y times y, y squared. Y times negative 1, negative y. 1 times y, positive y. 1 times negative 1, negative 1. But then I still have this plus y plus 1, right? Plus y plus 1. And some things cancel, right? This negative y plus y cancels. This negative 1 plus 1 cancels. And I end up with y times y minus 1 on top. And then on bottom, I have a y squared plus y. That's the stuff that's left. Y squared plus y. Ignore this page number 2. Yeah, there you go. And looking at the bottom here, I notice that there's a GCF. Looking at this denominator, I can factor out a y. Their GCF is y. And so I get a y times y minus 1 divided by a y times y plus 1. And because I factored that GCF, I can now cancel the factor of y that remains here. And I'll write my final answer really cleanly. My final answer is y minus 1 divided by y plus 1. There you go. That's the final result. Okay, so this lesson has been useful in helping you to simplify complex rational expressions. That's when we have rational expressions inside of rational expressions, a fraction within a fraction. And this is the process that we can use. And you actually learn two different versions. Okay, adopt the one that you like best. But please be aware, sometimes one version works better than the other version, and so it's good to know both. Anyway, have a wonderful day. Take care.